In this video, I'm going to talk about non-dimensionalization. This is a real word. It's in the index in the Strogatz book, and it refers to dimensions in the sense of units. So dimensions as in length, time, mass, and count. And in the metric system, you will see meters, seconds, kilograms, and then count would be something like how many people, how many individual organisms, um, things like that. And from these basic units, you can build, obviously, area and volume. You can also build speed and acceleration. You can also build force and energy and power. In more exotic type settings, you might need electromagnetic units. If you're doing thermodynamics, you might need temperature. But for some simple physical problems, these basic units will suffice. Now, the problem that I would like to set up is one that you have probably seen, which is a spring with a mass attached to it experiencing gravity. Now, I'm going to put in some constants there. For h is the height of the support up above, and I'm going to let y be a dynamic variable. That's the height of the mass at a particular point. And then the spring, just left on its own, has a preferred length s. The object hanging from the spring will have a mass m. So h, y, and s have units of length, and m is in units of mass. Let me make this a capital M, just so that we don't get confused with anything with meters, for example. Okay, now to set up the equations of motion for this, I'm going to use a form of Newton's second law, which says that net force is equal to mass times acceleration. Force is in units of newtons, and a newton, in order for this to make sense, must be equal to 1 kilogram times a meter per second squared. So that's a mass times an acceleration. The first force is gravity. Gravity is pretty straightforward. It is proportional to the object's mass. Let me use a capital M. And we're going to do this near the Earth's surface. So we need the Earth's gravity constant, which is the familiar 9.8 meters per second squared. And so you see there, we have a force in newtons equal to a mass times an acceleration. The negative sign means that gravity points downward. The next force that we have to deal with is the spring force. And the spring force is a little bit trickier to explain, because here's the situation. If the spring is stretched past its preferred length, then it exerts an upward force that's proportional by a constant of proportionality, k. Yeah, let me use a capital K for that, times the stretch, the difference in the length. So that's going to be calculated as follows. So the actual length of the spring is h minus y. The stretch is h minus y minus s. So stretch is h minus y minus s. So that's the amount here by which the spring is extended past its preferred length. And the force is upward, so I'm going to write that the force of the spring is k times h minus y minus s. And again, k, h, and s are constants. Y is a dynamic variable. Now, just so that you can see this is supposed to be a force, so it's in newtons. This is a sum and difference of lengths, so this is going to be in meters. That means that this has to be in the peculiar units of kilograms per second squared, so that when you multiply it by meters, you get kilogram meters per second squared. So let me write that down. K has units of kilograms per second squared. Okay, now when you write this out, you'll get minus mg plus k times h minus y minus s equals, so that's the net force. Mass is m, and acceleration is, I'm going to write it like this, d squared y over dt squared. So t is in units of seconds, and y is in units of meters. Now if you look at this, there's a lot of stuff going on. There's 1, 2, 3, 4, 5, well, 5 different constants with different units. And there's there's one dynamic variable and one independent variable. And looking at the equations of motion this way kind of obscures what's going on. So here's what we can do about this. So first thing I'm going to do is divide through by m. That gives me minus g plus k over m times h minus y minus s equals d squared y over dt squared. The reason for doing that is that at this point, the only place that kilograms, mass, appears in this equation is right here. K is in units of kilograms per second squared, and m is in units of kilograms. So the kilograms, the mass part, is entirely contained here, and it actually cancels out. So everything left is just length and time. Next thing I want to do is adjust y, and I'll show you why that happens here. So let me first expand all of this out. So we have minus g plus k over m times h minus s minus k over m times y equals d squared y over dt squared. Okay. Now I want to adjust y so that I can get rid of this term. This is not technically non-dimensionalization, this is kind of a change of coordinates. But if I let z be equal to, let's see, what do I want? I want y plus h minus s. Then, no, I want one more thing, don't I? Oh, wait a minute. Yes, no. Do I want to do that? Do I want to include... No, I want to include the g in here as well. So let me rewrite g over here as well as k over m times minus gm over k. And I want minus gm over k. The point of doing that is that all of this stuff is constant. So dz dt is equal to dy dt, and of course d squared z dt squared is d squared y over dt squared. But once I put this in for y here, you'll see what happens. So I've got all this stuff, k over m. I'll go ahead and just kind of club it all together. That's probably not a real word. I'll have to look it up later. Do I have the wrong sign in here somewhere? Yeah, I think I got it backwards. Sorry. What I wanted was this. Okay, that's what I wanted. Okay, that's what I wanted. I wanted instead y to be equal to z plus that stuff, because when I substitute in for y here, you can see that all of this stuff matches all of that, and it's all going to cancel out. So the end result of this is going to be zoop, 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 k over m minus z equals d squared z over dt squared. Now, another way to see how this is supposed to happen is that if you let the system come to rest and you set z equal to 0 to be the position of the object if it's just at rest and not moving, then you'll get the same change of coordinates here. This was an algebraic way of deriving that. Now, remember that k had these peculiar units, kilograms per second squared, and m has units of kilograms, which means that k over m, oddly enough, has units of 1 over second squared. So I'm now going to change time variables. Now here's how this works. If I take d over d tau of z, that will be, sorry, let me do it the other way. I'm going to say dz over dt equals, and I'm going to use the chain rule. I will insert a new time-like variable d tau, like so. And furthermore, I'm going to assume that tau is equal to just some constant times t. So that gives me dz over dt is dz over d tau times c. Taking the derivative again with respect to t, I get, well, the derivative of dz over d tau with respect to d tau times d tau over dt times c. So what I've just done here is the chain rule applied to this new independent variable dz over d tau. So the end result of this is d squared z over d tau squared times c squared, because I get a c here. Now, I want tau to be dimensionless, so I need c to have units of 1 over seconds. So that way c times t, the seconds cancel out. Now I go back over to here at minus k over m z equals d squared z over d tau squared times c squared. And now I'm going to divide through by c squared like this, which is going to give me negative k over c squared m equals d squared z over d tau squared. Now, by the way, I probably should not have used c for this in hindsight because mc squared looks like Einstein's formula. That's not what's going on here. C is not the speed of light. C is 1 over a time unit. And if you look at the, oh, where did my z go? There should be a z right here. If you look now at this, remember k has units of kilogram per second squared. C has units of 1 over second squared, and m has units of kilograms. So if you build up kilograms over c, sorry, I said that wrong. C has units of 1 over seconds. So if you build up k squared over k over c squared m, you're going to get kilograms per second squared over 1 over second squared times kilograms. And everything cancels out. So we are left with one number that is unitless. And I'm going to, since this number is positive, I'm going to let this be omega squared. And let me be speak here, this is a big C. So at this point, we have written a differential equation that captures the essential behavior of the physical system. But Z, let's see here, does Z have units? I think Z might have units still, but we can divide through by the units of Z. So we can just divide, we can just come up here and say, where did we define Z? Yeah, we can just say that Z, we can divide all of this by 1 meter. And now Z has no units. You should recognize this as the equation for a harmonic oscillator. And from here you can solve it. The solutions to this are of the form A cosine omega tau plus B sine omega tau. There's other ways of writing them, but these are the simplest ones to remember. Now, as to why is all of this important? When you use an analytic function that's defined by an infinite series, so functions defined by infinite series should be applied to dimensionless numbers. So for example, cosine of 5 meters doesn't make sense because meters is a unit of length. The reason for this, right, is that cosine of theta, for example, is defined as follows. Well, sorry, not defined, but it has an expansion as follows. And if you look at this, the 1 has no units attached to it. If theta had units, say length, this term would have units of area, and this would have units of some kind of 4-dimensional hypervolume. And you can't add those together. The units of two numbers, two-dimensional numbers, the units have to be the same type. They have to be compatible in order to add them together. Multiplying and dividing is not a problem, but adding together unit quantities, it only makes sense if the units are compatible. So cosine, the trig functions, the exponential function, um, the logarithm, those are the ones that show up the most often. And you need to be sure that you are applying them to, to numbers that do not have unit dimensions. If there is something in there that where you want it to be there, then you need to put in some kind of a constant factor that can convert it out of those units and into a dimensionless quantity. So for example, up here, if you really wanted to go back and write this for y, you would have, so y is equal to z times 1 meter. So that would be a times 1 meter times cosine. And now omega is the square root of that. So we would need square root of k over c squared m times, and then tau is, what is tau? Tau is c times t. So I need this times c times t plus b times 1 meter sine of the square root of k over c squared m times c times t. And it actually cancels out. The c here will cancel out with the c squared under there, and that will leave you with, oh, I forgot, plus the offset. So we have a times 1 meter cosine square root k over m times t plus b times 1 meter times sine of square root k over m times t plus a length, which I need to get from back here. Where did it go? Right here. Okay, and you can see that again, k over m will have units of 1 over seconds squared. So then the square root of k over m has units of 1 over seconds. So then when you multiply square root of k over m times t, you get 1 over seconds times seconds, which is dimensionless. So it's okay to compute that cosine. Same thing happens for the sine. So that's an example that should be familiar of non-dimensionalization. Another technique that you will sometimes see that's a little bit more ad hoc, but hey, physics can sometimes be that way, is to write down all of the things that you have in the problem and the units that they have and try to find some product quotient of them that has no units. Or, for example, maybe something that has length units. Sometimes that will give you a characteristic length scale for the problem. So, for example, if we're looking at this problem that way, let me switch to a different color. We have the gravity constant, which is 9.8 meters per second squared. We have k, which is, we don't have a specific value, but it is in kilograms per second squared. We have h and s that are in meters, and then we have time that's in seconds. So if we wanted something that had some kind of characteristic time scale, oh, and I forgot the mass of the object. So mass is in kilograms. So if we wanted something that was kind of a characteristic time scale, then one thing we could do is to combine these and see again that if you do m over k, that has units of kilograms over kilograms per second squared, which is really equal to just seconds squared. And so then the square root of that will come out in seconds. Yeah, I generally been using the colon to indicate units. And so that indicates that this is some kind of characteristic time scale. And if you work it out, that is indeed a characteristic time scale for this system that is related to the period. If you go back down here and look at this, it repeats. It repeats when square root of, let me write this a little bigger, when square root of km times t is equal to some multiple of 2 pi. So if you want, this is saying that it repeats when, I'll divide it over. It repeats when time is an integer multiple of 2 pi times the square root of m over k. So in other words, this is the dimensional period in, this is the period in seconds of the oscillations. So the square root m over k is not in itself the characteristic timescale, but it's a multiple of the characteristic timescale. Okay, so there you go. That's non-dimensionalization in the example of a mass hanging from a spring, classic introductory physics problem. In more complicated situations, you may have to come up with more complicated arguments to reduce the number of parameters and get them down to a non-dimensional form, but this is at least a good start.